Hi, I'm Jiaye Leng from City University of Hong Kong. Today, I'm going to present our work, ProInterAR, a visual programming platform for creating immersive AR interactions. This is a collaborative work with Jiaye, Pengfei, Karan, Singh, and Hongbo. Augmented reality blends the virtual and physical world seamlessly. AR interactions, such as games and tools, have redefined the way we live, work, and play. A typical workflow to create an immersive AR application requires creators to traverse among building AR scenes, writing codes for interactive behaviors, and testing from an AR-HMD. It's not easy for novice AR creators, since it requires users to have good coding skills to script interactive behaviors. Real-world contents and their behaviors are hard to access using desktop interfaces. Creators need to traverse between multiple platforms and scenes. So, how to smoothly fuse AR contents in programming remains a question for novice AR creators. In this work, we aim to handle programming general AR interactions among real and virtual contents and enable complex interactive paradigms, especially between the real and virtual contents. Since there is no framework discussing the possibilities and boundaries of general AR interactions, we first develop a design scope. It describes general AR interactions from 4 dimensions. AR contents can be divided into 4 subject types: real objects, virtual objects, real environments, and virtual environments. Any AR interaction can be decomposed into basic interactions happening between 2 subjects of the same or different types. AR interactions can be used for various usage scenarios. Most of the existing works focus on the interactions of a certain domain, like gesture AR or toy-based interactions. Recent works like Leng IoT VR and Flowmatic are proposed for creating general VR interactions. However, they focus on scripting interactions among virtual contents in virtual scenes. From the time perspective, AR interactions can happen serially or parallelly. In the serial mode, one interaction follows the completion of the previous one. In the parallel mode, AR interactions can occur simultaneously. An AR interaction can include a range of logic flows, varying from simple to complex. In simple cases, the logic flow may involve straightforward and linear sequence of steps. In complex logic flows, it may contain branches, loops, iterations, time control, and multiple conditional statements. In this work, we aim to support programming general AR interactions, covering all types of AR contents, enabling parallel and complex paradigms. So we proposed ProInterAR, a block-based visual programming system with an integrated tablet and AR-HMD interface. It consists of 3 components: a scene creation UI to create AR contents from an AR-HMD, a visual programming UI to specify the AR interactions from the tablet, and an execution and controlling UI to experience the AR interactions from the AR-HMD. Then I will introduce them respectively. In scene creation UI, the creator can specify AR contents for interaction. By dragging a bounding box, a physical object is specified and updated in tablet. It can be tracked when grasped by hand. Use hand palm gesture to create a plane to specify planar real environment. Multiple planes can be grouped to form a compound environment. use a pointing gesture to specify curved surface. The creator can drag the virtual object from the library. Besides contents, multiple types of argument values can be created and passed to the tablet for selection. In visual programming UI, the creator can program the interaction of the created contents by stacking the blocks. Finally, the creator can execute and test the program. Here, we use the AR game Walker mode to show the creation workflow. To start, the creator first creates a virtual hammer and a mole, and specifies a physical cup and book, and a box zoom for interaction. Then create a score to count the game score. Then place virtual balloons in mid-air. Then in programming, for hammer object, add an if condition block for collision detection. If collide, then score increases. And add a go to random position block to the mole. For the remaining objects, add conditions that when hit by the hammer, score decreases. And add a grasp event to the hammer. Run the program and a mole starts to appear at random locations. Grasps the hammer to hit the mole to increase the score. When it touches other object, the score decreases. ProInterAR can be used for various application scenarios. Here we show 4 examples. Users can build AR instruments using physical objects and padding to play different sounds. Teachers and students can build their own AR learning and experiment contents. Users can create sequential animations containing multiple conditions and sequential triggering. AR information visualization can also be achieved using ProInterAR. To evaluate ProInterAR, we first conducted an individual evaluation. We recruited 12 participants, including 10 university students, 1 child, and 1 teenager. They mainly were novice AR creators. They were asked to create 2 AR applications using ProInterAR, one game-related and the other non-game related. After the creation, we asked them to fill in questionnaires and interviewed them to discuss their using experience. The results shows our system is good at creating general AR interactions. Within 25 to 40 minutes, they covered extensive scenarios, including AR games, AR animation, AR tutorials, AR navigation, AR shopping, interaction prototyping, AR measurement, AR fitness. Here, we show several of their created applications.
Impression. Sunrise is an 1872 painting by Claude Monet, first shown at what would become known. The Starry Night is an oil-on-canvas painting by the Dutch post-impressionist painter.
The SUS and NASA TLX scores indicate that our system has good availability and low workload. We further analyzed the record interviews using semantic analysis. 6 main themes were emerged. Participants expressed their preference for combining tablet interface with AR-HMD, which provided an immersive and flexible environment for in situ authoring, and ProInterAR retained a similar logic as traditional coding, but the block-based programming lowers the barriers to use. The kit participant find it interesting and useful to allow her to understand complex coding logic intuitively. However, participants shows that ProInterAR has a slight learning curve, especially for those with limited programming backgrounds. Thus, we further conducted a long-session evaluation to investigate the learning effects. We recruited 2 more participants who were not part of the first study. One had no AR creation experience before, while the other had created several AR applications. Unlike Study 1, they were asked to create an AR application as complete as possible within 5 days, and we had interviews with them to gather feedback after each day's task. Here are a short clip of their created results: an office assistant publication and an adventure game. From the interviews, they expressed their fondness for ProInterAR. P1 believed that this block-based programming had reduced her cognitive burden and made her full of confidence in learning real programming. Moreover, the creation of AR application had strengthened her emotional connection with objects around her. P2 believed that ProInterAR was very useful for in situ authoring, with portable devices offering a good balance of precise control, display clarity, and support for mobile use. Also, he pointed out the potential errors and debugging burden that could result from the differences between ProInterAR and traditional programming. ProInterAR also has some limitations. First, physical simulation has not been supported in our current system. Participants expected to enable the created objects like the ball and the arrow with gravity effects to enhance the reality. We can introduce a fourth system to our system in the future. Second, currently we design the programming blocks as fundamental concepts, allowing users to stack them freely. It sometimes requires creators to stack the blocks for similar actions repetitively, like the direction buttons in this figure. To improve it, we can introduce the wrapped block components with predefined functions. Third, we allow users to track the 6 DOF pose of physical objects according to the user's hand pose. However, for automatically moving objects and precise shape estimation, our approach doesn't work. In the future, we will integrate more robust and flexible object detection, tracking, and shape estimation algorithm into our system. To sum up, we developed a design scope that describes general AR interactions from 4 dimensions, proposed ProInterAR for creating general interactions, demonstrated 4 application scenarios, and evaluated our system through 2 usability studies. If you have any questions, welcome to contact us. Thank you.